This lecture, we're going to get more in depth about CUDA programming. We're gonna start writing our first kernel in the Nvidia GPU, and we're gonna write this code in CUDA using C++. We will also use Python. In this case, we're gonna use C++. So first, what we're gonna do is we're gonna include our standard library for input and output. We're at iStream, there is a standard library in C++, and then we need to include CUDA runtime.h, this header, and all of the kernels in CUDA need to have this macro of global first. Then we, as usual, we just indicate the return type we're gonna do void, and the name of the kernel is gonna do vector addition, and the parameters that we're gonna have is float, and all of the values that we're gonna pass here are gonna be type float. So we are going to pass in the kernel, the parameters are basically going to be references of the value, as we're gonna pass them all as pointers. Here we will have the variables for the different vectors, and finally we will have, and that will be the number of threads. This also need to be an integer, as this is just like a size of the threads that we're gonna be using. We're gonna define our global index for accessing the X direction. So we already saw in assembly code in PTX a little bit about this. So in order to access the array in one dimension, for example, in the dimension X, we need to specify with the block ID and the block dimension that this could be seen as a matrix array of 2 dimensions, that we will have uh, the this syntax in order to traverse the array. So what we will have is basically uh, moving through the block dimension and then just adding like this offset. That will be our thread ID. Let me see if I can share a picture to make this clear. Okay, here we have a picture where we can see here how it works. So if we were in the X dimension for like the dimension of the block, we will see here that our block dimension, for example, in this case, will be 4. And with the thread ID, we will be moving to the specific thread in the X dimension. So we see that this green thing here that we can see here is our entire grid. These are the blocks. So here we have block dimension of X equals 4 because we have 4 threads here. So the way it will work here is that we will have the block ID 0, 1, etc. with the block dimension. If we are here um, in the first ID, then we'll be in 1 with a block size of 4. So if we are in this block, for example, that is the 1 comma 2, because we are in the X direction. We are in the second position, that this is indexed from 0, so we will be 0, 1, 2, and 3, etc. So we will be in the first block with the dimension 4 index direction plus 3, because here we will be in this thread. So this is how we will access all of the different elements. So this is the global index to access the different elements in our array. So here we will indicate an if statement that if our global index is less than the number of threads, then perform the addition that will be of this way. So this will be our kernel. Then in order to call this function, we will indicate the number of threads here, that we will indicate the number of threads of basically 1 kilobyte 1024. We will indicate the size that we need to allocate in our arrays. That will be the number of elements multiplied by the type of variable. So we will need n amount of float variables, as this will be the type of our elements that we're going to store in our array. Then our arrays will be pointers that we will indicate for A at H of host, as this will be the CPU part first, and then we will allocate the memory for this, same for the array B and for the array C. This will be for the host. Then we are going to initialize the elements for the n elements. We're going to initialize H and B, as these were allocated with the dynamic memory allocation. We're going to initialize them to avoid different problems with memory leaks and so on. We're going to do a casting of floats, as this index is of the type of variable integer. Then we will define our device variables, that they're going to be the device for the array A, B, and C. We're going to initialize these variables. So it's correspond. So here we will have the initialization of the arrays in the device. Then we're going to define our error structure. We will define this variable error, and here we're gonna assign that we are going to allocate the memory for our array in the device A. Oh, here I'm missing that this is a pointer. So what we have here is that we are initializing the memory now for the device with CUDA malloc. We are doing this casting for the different arrays, in this case the A, and if we have an error, meaning like we don't have CUDA success and we're gonna exit, we're gonna allocate the memory in the same way for B. If we do not have a success, we're gonna free the memory of D, as we already allocated this memory here. In the case of C, we're well, like free the dynamic memory for A and B that were successfully allocated previously. After allocating the memory, what we will do is use CUDA and copy in memory of the array in the device A. We will copy the contents in the host in the array A for the size that we already defined, and we will define CUDA memory copy host to device. And we're gonna do the same for B. Then we need to call the kernel that we named here. And then something that we need to define here is that we need to pass two parameters to the kernel when we're gonna launch it. We need to pass the number of threads by block and the number of blocks. So remember we have a total number of threads of 1024. So what we will need to do is that to define the number of blocks that we will have, we will use this formula. We will use the number of blocks will be the number of threads first that we define in our variable n. We will define the number of threads per block -1 and the number of threads per block. That indicates that we're gonna divide the variable of threads into 4, that we will have basically 4 blocks. So in this case, if we, for example, let me do real quickly. That means that if we have this number of threads and we divide by 4, we will need to have this value here. We're gonna subtract 1, divide by this value, and then that will give us 4 blocks, and each block will have this amount of threads in the block, and then we're gonna call the parameters of the kernel as we launch it, and we will have the device array, the device array B and C, and the number of blocks. Then we will call the function CUDA device synchronize in order to synchronize here before writing into our register in the device C. So we will we don't write until we have the results ready. We are going to make sure everything went smoothly and correctly, catching the error in the last operation that we had. And here in the conditional, if this wasn't a success, here we will print in the error output. And that will be all for this condition. Finally, we will copy the contents of in the host C of this kernel operation. That will be we will have these results stored in the device C, so we are copying them back to the device, to the host in the CPU. And after having this, same, we're gonna get the last result in this operation. And here we will have a message that it failed to copy the result back to the host. And then in order to print the values from the host to make sure everything went correctly, we will have this for loop to iterate through the elements of the host C. And for that, I'm gonna print up to 10 elements. So for this, I will be printing with cout the contents of the elements in the host C, and that will be all for this code. And then finally, I just need to free the memory for the arrays in the device and the host, and that will be for our code. Finally, something that we will need to do is compile our code. For that, we are just going to call nvcc. We are going to call the architecture that we have, as mentioned before. So I have the architecture of like RTX 40, 4090. I'm gonna call streaming processor 89, and then I'm gonna pass the flag of PTX to generate the PTX code, and we're gonna specify the function. I see here the results, and I have here the assembly code of this, and that would be all for this case. Then something that I can do is that I can like see how this executes this code in the PTX representation. So to generate an object, something that I can do is PTX, call this PTX AS, call my architecture, that will be streaming multiprocessor 89, then call my intermediate representation of the code, and with this generate kernel that I'm gonna call addition, kernel addition, and we have the extension of Cubin. So as we can see, we cannot open like this binary code, but we can see here this function, and we see like the kernel here is specified here as follows. So something that I could do is in my host, for example, I have here to run my kernel in this object binary. Something that we need to do is call in the CUDA model load, we would just call our kernel, that in this case will be addition, and I will just call the kernel here. And then finally we could just compile this code. That could be this. Okay, let me pass the link for CUDA. And then execute. And as we see here we have executed our PTX code.